Hello and welcome to the recrystallization of benzoic acid. In this lab we're going to take two samples of benzoic acid. In a pure sample we're going to take 0.5 grams of that approximately and recrystallize it, as well as an impure sample. To start out, we're going to take a pure sample of benzoic acid, weigh out the recommended amount of that. First, on the scale, we've got a weigh boat on the scale. We've got that zeroed. That way when we add our benzoic acid, that scale is reading the exact weight of benzoic acid that is being added to the weigh boat. And on the scale, it looks like we weighed out 0.52 grams. So 0.52 grams of impure benzoic acid is now being added to this small Erlenmeyer flask. And we have water that was in that beaker, which has been preheated, so we are close to the boiling point of water. And that water is now being added to the Erlenmeyer flask, so we can dissolve all of the benzoic acid and recrystallize it. So it looks like what we've added is not yet enough to dissolve the benzoic acid. It's a relatively hot solution, so it's pretty clear that we're going to need to add a little bit more. It's crucial that all of the solid dissolves in the solvent. If not, it's impossible for anything that remains undissolved to then recrystallize back out of the solution. As you can see, all of the benzoic acid is not yet dissolved in that solution. Also, it looks like we have much less than 20 milliliters of water in that solution. So looking at the calculation that hopefully you've already done, but if you haven't or need some help on that, here's some help. So if we have 0.5 grams of benzoic acid, we know the solubility of that is 21.5 grams per liter at 75 degrees Celsius. And if we then, once we convert grams to liters, if we convert that to milliliters, we know that we need 23.3 milliliters of water at least to dissolve all that benzoic acid. So we need to add more water, which we did there. It was cut out of the video, but more water was added to make sure that all of that benzoic acid dissolves in solution. And still, you can still see some crystals at the very bottom of that Erlenmeyer flask, so it is not yet all dissolved in solution. We're getting a little bit closer now to it all being dissolved, but you can still again see some tiny crystals in the bottom of that beaker. Alright, after being on the hot plate a little bit longer, we ensured that all of those crystals were dissolved in solution. We couldn't see any more solid in solution, and now we have an opportunity to grow crystalline structures of benzoic acid. We want to grow those crystals slowly, so that's why we put that on the bench top instead of putting that directly in an ice bath. If we can allow those intermolecular reactions to essentially slowly accumulate, we can form a more pure stacking pattern, making a more pure crystalline structure of that compound. So once it's cooled down to about room temperature, that's a good time to go ahead and put that Erlenmeyer flask in the ice bath to make sure we have plenty of crystals forming. Now, considering that some crystals were already forming once we put it on, after we let it sit for a while at room temperature, we probably could have let that go a little bit longer, and that would have given a slightly more pure sample. But to speed things up, to make sure we get out of lab in time, it's okay to go ahead and put that on the ice bath. And at the end, you probably want to do that anyway to ensure that we are maximizing the amount of benzoic acid that recrystallizes out of solution. Right now, the vacuum filtration apparatus is being set up. So we have an Erlenmeyer flask with a sidearm. We're putting a tube on that sidearm and connecting that to the output of the water faucet. So when we attach that there, that does not mean water is going to the Erlenmeyer flask. That means water is going straight down into the sink and pulling air or pulling a vacuum suction from that hose as water goes down into the sink. Now that it's been 10 or more minutes of our benzoic acid recrystallizing in the ice bath, it is just about time for vacuum filtration. So we've got the water faucet on, pulling suction through the vac filtration apparatus. We had our filter paper wet and at the bottom of that vacuum filtration apparatus. And now we're pouring the mixture of benzoic acid crystals and the solvent water onto the filter paper, allowing us to isolate our crystals. Ideally, instead of swirling that around, you'd take a metal spatula and lightly scrape that out, and then maybe also try to just go ahead and just dump it all through there at the same time. The more you jostle it, the more likely it is those crystals are going to dissolve back in solution. Also, using water, definitely use a pure sample of water. So ideally what you do is get an ice bath and get deionized water and have that deionized water cooled down in a separate beaker in an ice bath solution. The ice that's in the ice bin in the lab is not a pure solution of water, so that'll essentially cause contamination, and we're actually going to see some contamination most likely when we assess the melting point later. So we had those crystals isolated on that filter paper. Those dried over the week, so we obviously aren't going to show a recording for a full week. We'll assess that later. Right now we've moved on to the recrystallization of the impure benzoic acid. So on your worksheet, on your lab handout, it says to get approximately 0.8 grams of the impure benzoic acid. So we'll see what we end up with. All right, it looks like 0.82 grams of impure benzoic acid. Again, 0.82 grams of impure benzoic acid is currently in that weigh boat. We're going to add that to a small Erlenmeyer flask. And for this recrystallization, since we're recrystallizing impure benzoic acid, that means we definitely have other compounds in solution. So instead of just trying to form an ideal crystalline structure of benzoic acid, now we're trying to do the same thing, form a crystalline structure of pure benzoic acid. We also are hoping that any impurities in that solution, so whatever compounds are also in that initial solid, remain dissolved in the aqueous solution. That's why it's more crucial than ever that all of the solid dissolves in solution. If any solid is left, that's going to be a mixture of the benzoic acid plus any impurities, and then when we isolate the solid, that means that we would have isolated impurities with that solid, which defeats the purpose of recrystallization. At this point, it looks like everything is dissolved in solution, so there's no more solid in solution. We're going to put that, let that cool down to room temperature. We want to make sure it cools down to room temperature so that the crystals can slowly grow. So in this case, when those crystalline structures grow, we need to make sure that the impurities are excluded from that crystalline structure. Once that cools down to room temperature, if nothing's happening, then at that point you have to just go ahead and put it in the ice bath. If crystals are starting to form, maybe leave it at room temperature for a while longer, but if it's been a long time at room temperature and nothing's happened, then you got to put it in the ice bath. So in this case, again, we want to have that on the ice bath for at least about 10 minutes. Once that's there, hopefully we've formed plenty of crystals. Now it looks like in this case the crystals are pretty much overtaking all of the volume in that flask. So it might have been better to have a little bit more of our recrystallization solvent water to make sure that all the impurities remain dissolved in solution. So in this case we have a very small amount of solution. So I wouldn't be surprised if this didn't end up being a very pure sample of recrystallized benzoic acid. Again, I would recommend using a metal spatula to scrape that out. And definitely make sure you use a pure water solution. So you definitely, as was done in the video, you do not want to take directly from an aqueous solution that has the ice in it. That ice is not pure, and that is also going to cause some additional contamination of those crystals. We'll see what our results look like when we assess the melting point. So in this case, we actually had a larger mass of solid initially, and you can see that within the vacuum filtration apparatus, things are a little bit slower. It's kind of stuck in the apparatus, so we're going to have to let that water run a little bit longer before it's dry enough to set out for a week before we assess the melting point. So now it's a little bit more dry in there. It's probably good to go ahead and turn off the water, leave that in your drawer for a week. So at this point, we're really done with that day's lab. So we have done the recrystallization, we isolated those solids and let them dry. So now coming back the next week, this is where we are going to assess the percent recovery of our two recrystallized compounds. So the first one we're going to assess is the recrystallized benzoic acid from the pure benzoic acid sample. As the crystals dry on that filter paper, it actually makes it quite a bit harder to scrape off. Sometimes it's better to go ahead and scrape that off into a weigh boat on the day of the lab rather than keeping that whole Buchner funnel. So it looks like we have 0.40 grams of the recrystallized benzoic acid from the original pure benzoic acid. So again, 0.4 grams from the original 0.52 grams of benzoic acid. So now we are to the point where we are scraping off the recrystallized benzoic acid from the impure mixture. Another reason why it's sometimes good to scrape it off originally, because sometimes it's easier to get the solid off, because you can see some of that paper is kind of crumbling or degrading a little bit. So there could be some additional impurities because of that filter paper. All right, so we have 0.65 grams of the recrystallized benzoic acid from the impure mixture that we did last week. Now we're to the point where we're going to assess the purity of these compounds. So we have a melting point standard. We have benzoic acid, which is our melting point standard. And we have recrystallized pure benzoic acid. So benzoic acid recrystallized from the pure benzoic acid compound. And we also have recrystallized benzoic acid from the impure mixture from the previous week. So right now we're getting some of that solid into the melting point capillary tubes, which have an open end and a closed end. So essentially we're adding a little bit to the open end, tapping it down so we have a small amount of solid at the bottom of the closed end. So now that we have all three samples prepped, we have our benzoic acid standard on the left, our recrystallized benzoic acid from the pure sample in the middle, and our recrystallized benzoic acid from the impure sample on the right. So this phone camera is looking right into what you would be looking through into the melting point apparatus to see our actual compounds melting. Now, the only problem with this is we cannot simultaneously see the thermometer. So ideally the thermometer would be slowly rising and be able to get a temperature. I have some graphs at the end to show the temperature, but this is a great visualization of what this looks like when you're actually looking into the mel-temp apparatus. So, like I said, we can't see the thermometer, but the temperature is slowly rising. So eventually we expect to start to see some liquid somewhere, and at that point we'd want to look back at the thermometer and see the exact temperature where that liquid started to form. So as it gets warmer and warmer, you can see it start to settle, and it looks like the one on the right, it looks like some liquid is already starting to form. So I can actually see a little water droplet down there at this point. So I would say liquid had started to form a couple seconds ago. So you'd look at the thermometer, see the starting temperature, and it looks like that's still in the process of melting, but not done yet. I still don't see any liquid form in the middle one or the one on the left, so or recrystallize or the one on the left. So now it looks like the bottom of that, the one on the right is all melted. So I would say look at the thermometer, see the end temperature, and now it looks like the one in the middle is starting. I don't see any liquid yet for sure. Okay, now I definitely see some liquid there in the middle one. You can see essentially the bottom of that capillary tube has some liquid in it, and then the one on the left is starting to melt too. So the one on the left has started, the one in the middle is about in the middle of that process. So even though we're looking at this for a long time, it could take a while for the thermometer to rise in temperature. So the temperature change might not be that much. You'll see on the table what my guess as to what it is. So it looks like the one in the middle is still melting. The one on the left definitely started about 10 seconds ago. The one on the middle is all melted now, so I'd say that all of the solid has turned to liquid. Specifically, we're looking at the bottom, so you don't want to look too high at the top, because if you do, the temperature isn't that high up there. So you really want to look at the bottom and see when that is all liquid. And now the one on the left, we're very, very close to the end. There's still some solid at the very bottom. There was a little bit too much compound put in there though, so based on that, as long as everything melts very soon, I would probably call about right now the end temperature for that. And yep, everything is now close to fully melted. Okay, yep, that one's fully melted at this point right now. So if there was less in there, I'd wait till it was all liquid, but since there was so much, especially so much up high, I would say that one, I would have called that one down a little bit early. Looking at this melting point table, we have our three samples, so our benzoic acid melting point standard, the one on the left, the benzoic acid recrystallized from the pure compound, which is in the middle, and the benzoic acid from the impure mixed, which was on the right. The standard values for all those are the standard melting point value of benzoic acid, which is 122 to 123 degrees Celsius. So for our experimental values, those are already entered. So essentially, based on the start temperature when we started to see some liquid in that capillary tube to when it was all liquid at the bottom of the capillary tube, that's how we assessed what those numbers are. Now, for the corrected value, that is only based on the melting point standard. So that benzoic acid that was on the left, that was essentially a known pure sample of benzoic acid. So that wasn't an additional test that we were doing. That is what we're going to use to adjust the thermometer if necessary. And based on the value of 120 to 122, it looks like our thermometer is reading a little bit low because we know that benzoic acid should melt at 122 to 123 degrees Celsius. So we want to make the end value of our experimental values match the standard for the benzoic acid melting point standard. So to do that, we need to add 1 degree to make, instead of 122 the end value, we need to make that 123. So when we add 1 to that, we add 1 to both the start and end value. That gets us to the corrected value of our melting point standard, and then we do the same thing for our experimental values for both compounds that we assessed. So now we are at the point where we can analyze the corrected melting point values of our isolated compounds so that we can then assess whether or not they are pure. And from what you can see, it looks like our recrystallized pure benzoic acid is still not as pure as the melting point standard, and our recrystallized benzoic acid from the impure sample is definitely not as pure as the pure sample because it has a much lower and more broad melting range. So from some of the things we talked about, maybe not enough solvent being used, washing with an impure solution of water rather than a pure solution of water, both of those things, as well as a few other things, could have led to the impurities in our isolated crystalline compounds.